Hello and welcome to the next tutorial. This time we create a font atlas. Remember that you need to be on the branch 13 font atlas. I'll put the link in the description. The easiest way to get font showing in the game is to use a monospaced texture. You can see me creating one here. It is a 80 by 80 texture that is divided into a grid of 5 by 10 pixels. Every character is 3 pixels wide and at most 6 pixels tall. This means that there is space for 128 characters in this texture. It fits perfectly with the ASCII table, meaning that later we can use the characters in our program to index into this texture. If we are not using any special characters, we can just use their number. Every character has a number associated with it. And then use that as an index into the rows and columns of the texture. I will show you how we do this later on. If you like what I do, consider tuning into my Twitch. I stream at 10 AM Central Eastern Time, which is 1 AM Pacific Daytime. If you want to directly support me, you can do so via Patreon. This will give me more time to work on my game Cakes to D, and you will get reading access to the GitHub repository. Patreons will also be called out at the end of every video. Subscribing and leaving a like also helps a lot. Thank you very much for your support. So yeah, thank you very much for Felix F, Meo the writer, Devil's Drop, and Michael Phillips. Additionally, pixel art I publish on itch.io will also be available for Patreons. Once we have the font atlas saved to a PNG file, we can import it using the drag and drop, and we can then locate it in our folders, which is the font atlas mono 5 to 10 DDS. The next thing we need to change is the assets.h file. We need to get what is called a struct texture. And this texture will tell us how many pictures it holds. A texture, in my opinion, is a collection of sub-images. And so this texture will have a vector of size. That would be the entire size. And then a vector of sub-size. This is how many sub-pictures we have in the texture. And when we define it that way, sub-size will be a size that fits perfectly into the size. If I have a width and height of 10, a sub-size could be 5. Or sub-size could be 2. It needs to be divisible. And then down below here where we get the texture size, we don't get the texture size anymore, but we get a texture. And let's call this get texture instead of get texture size. Then we obviously need to change that in the assets.cpp. So we go to that. Instead of get texture size, we have get texture here. And we return a texture. And over here we have a vector. Change that to texture too. Boom. And that will be a texture too. So instead of size, let me just quickly rename. You can do that by pressing F2, texture, boom. Now that should all be texture. Apply this, yes, please. And for the white fireball and pedal, we'll just set the texture dot subsize to texture dot size. And also I forgot, this has to be texture dot size. Quickly add that in here, the size, and then paste the subsize below texture dot size here. And then for the last case, we need to create a new one. This would be the asset. I guess I'll call this Sprite font atlas. Now for the texture size, we'll talk about this in a second. We first need to create that type. So go back to the asset ID and the assets.h and create the asset Sprite font atlas like this. Okay, so we are scaling our pedals arbitrarily, meaning that in actuality, the pedal is, I think it is 16 by 32, and we are scaling it to 50 and 100. We need to scale the font atlas too. And I know this is not perfect scaling. We should do a different type of scaling here. Usually what you would do in this scenario is you would have a world space where you could deal with the pixel sizes, the proper pixel sizes, and then a screen space in which you would actually scale these pixels to the screen. We will do that later because it takes an entire tutorial to understand, well, what does it mean to scale a pixel to the screen? And then we will also get into the wobbliness, which you might see if you pay attention, if you're moving very slowly. But for now, it is fine if we just scale this arbitrarily. And so I tried a bunch of values, and 240.0f by 240.0f sounded fine. And then that subsize would be 15.0f by 30.0f. So we're basically scaling this by 3, right? It's 80 by 80 and then 5 by 10. We are doing the scaling factor by 3. We could put a comment here, scaled by 3x. Okay, so once we are done with the texture size, we also need to load in the texture. So we add another case here for the asset Sprite font atlas. And this time we load in font atlas mono underscore 510 and return the data. Okay, that should be it for the assets. Now we are able to load the texture. Now to explain a bit what we need to do next, since we have a sub texture inside a texture, we need to transfer this information to the GPU, and therefore we need to change our transform on the GPU. The transform on the GPU will now know what the UV coordinates are for the textures to use and what the index, I call it animation index, into that texture is. For example, if we have two rows of 5x5 images in one texture, we would have an animation index of 6. Then the GPU or the shader should know or needs to calculate that it should only display the sub image at index 6 of these images. And I guess index 6 would be down here. So here, right, like this. And that's what we need to do. This is what we need to set up. So a transform needs to change, the transform on the GPU. For that, we go into the shared render types. And instead of having a size X and size Y, we also have a float. And I call these top V and bottom V. And then we have a left U and a float right U. So that's enough. Okay, so since we changed the transform now, I suppose the easiest thing to change next would be the shader. So go into shader.vert. Instead of using hard-coded UV coordinates, we use the transform. And since 0, 0 is left U and transform.top V, then we have left U again, transform.left U. And that would be, since it's 1.0, it is transform.bottom V. Then we have right U and bottom V. Transform.right U, transform.bottom V. And the last one would be transform.top V like this, and transform.right U. That's all we need to do in the shader. The calculation will happen on the CPU, which ones to use. And I suppose we can do that next. That would be the VK renderer.cpp. And I guess we have a bunch of errors. That should be because of the Win32 platform. That's Visual Studio Code. Don't get fooled. Wait a bit. Wait a bit. No? Still complaining? Okay. Good. Now, down here we add the transform. And I want to create a function out of this. Because it depends on the texture, the type of transform that we calculate. If the texture has no sub-images, so it's one image, then the transform top UVs and all of these UV coordinates, they will be the normal UV coordinates. And we will not only have entity rendering, but also UI and rendering. I consider entities and UI something different. And therefore, I consider font a part of UI, where you can do basically, well, display a text. Right, so we will have to generate a UI portion in our game as well. And we'll do that later. Hence, we need to generate a function for adding transforms. So basically, we extract all of this out and even the texture size as well. And instead of doing all that, we call VK add transform. That will probably take in the VK context and some other stuff that we'll see later. And I suppose we can just jump to the VK add render command in the file. And further below, we do an internal void VK add transform. And of course, we have a VK context pointer, VK context. We need that for sure. And we paste this in here. Okay, what do we need? We need a uint32t material index. Boom, let's supply that. It looks like we need to get the texture size. So we also need to have the asset type ID. Asset type ID, then use that. And this is no longer get texture size, but get texture. Therefore, this is a texture. Okay. And I suppose we can quickly calculate the sub UVs, right? So what do we need in order to calculate them? We need rows and columns. How many rows and how many columns does our text... Wait. Yeah, how many columns and how many rows our texture has. So we need a uint32t rows. That would be, if we take the texture size on X and we divide that texture by the subsize on X. And for the columns, we do that with Y. And I think I reversed those. Rows should be Y and columns should be X, right? So change those real quick. Columns and rows. And since we know a texture coordinate can be between 0 and 1, now we know how many columns we have. We just divide 1 by the amount of columns, and we know how thick one sub-image is in UV coordinates, right? I call this float UV width and float UV height. That would be 1.0f divided by float cols. Yep, and that would be 1.0f divided by float rows. Okay, now we have the UV width and height. And all we need to do is take in what is an animation index, I suppose. Let's just have a uint32t animation edx. And I suppose we, by default, set that to 0 because currently entities in the game do not have any animation index. And so they would just not use it, right? But we set ourselves up to use one later. Okay, so let me see. Animation index, the X position, what was that again? E origin, a sprite offset. I suppose we could supply a vec2 position here. And then we just set the transform X position to the position on X and the position on Y. And the size, I suppose we can also supply a size, a vec2 size. It would just be size on X and size on Y. Hell yeah, brother. Okay, now we need to get the top UVs, t dot top v. This is the top one. And I suppose we need the animation index here. We divide that by the amount of columns we have. Yeah, so if we have like 5 columns in the first row, we need to know, okay, so how many columns do we have based on the animation index? If we have more than 5, if our animation index is more than 5, let's say 7, and we divide 7 by 5, we get 1 point something, 3, 2 or something. And so we know that, oh, we need to go down 1 row. And so this would be the amount of rows we go down. And since columns and animation index is both an int and we want to have floats here, we need to convert that into a float. And then multiply that by the UV height. Okay, that's the first one. And then we have a t bottom v, which is very easy. It's just t dot top v plus UV height. The next one would be the t left u. That's the one that we have to calculate again. It's basically the same, and therefore I'll just type it out. We take the animation index. Instead of dividing, we take the modulo operator by the columns. Then we know, okay, that's how many columns we have. We modulo by those, and then we can only be in the range of these columns. And therefore that's how much, that's where the row is. Excuse me, this is where the column is. This is the part that we need to take. And then we multiply that by the UV width. And of course the t dot left, oops, t dot right u would be t dot left u plus UV width. Now one thing I wanted to add, this, let me center this. This calculation is done in integer values and this one too. Meaning that if we get like 1.2 here, if we would be able to get 1.2 here, the fractional part is being discarded because it's an integer value. That's why I chose to use ints. Very important. Because we want to know, are we in row 1 and not 1.2? That doesn't exist. We need to know, okay, it's 1, 2, 3. We want to have clean numbers. And then we add the transform. And I think this is it for the function. We have vk transform, we get the texture, we calculate the UVs, and we add it to the context. Okay, now we know what we need for the transform. We need a material index. Do we have that? We do. We have a material index. We need an asset type ID. We also have that. Position would be E origin plus E sprite offset. Hopefully it's plus and not minus. And I suppose we don't have an operator, do we? And then the E sprite size. Oh, I suppose we don't even need the size. We can just take the texture size here. Texture dot subsize dot egg subsize. Yeah, we can take the texture subsize. Quickly go back to the function and change that. We don't need to supply a size because we can get that from the texture. And we should use the subsize here. Okay, then go down. Well, going back to the vk transform here, the animation index for entities will be 0 and therefore left out. Okay, double check. I think this should be everything. I want to get back to feature parity and I see that the game CPP has some errors up here. Now we don't have a texture size anymore. We have a get texture on both of those. And I suppose what we could do is just take the subsize. Quickly check if that runs. Did I forget something? Well, it built. Failed to compile shader. Okay, we have a shader problem. Bottom V, no such field in structure. Okay, bro. Oh, I misspelled bottom, lol. I was like, huh? It was bottom. Needs to be bottom. Okay. It seems to be working. So basically we changed it to get the texture size. And we changed the shader to use sub UVs and the game still runs. That's very good. Then I guess we will go ahead and create a new folder in source. Call this UI. And inside that folder, we create a new file, ui.h. Let's pragma once that. And the first thing we want to do is create a struct label. What is a label? Like this. Okay, don't forget the semicolon. A label, in my opinion, is a char pointer with some text and a vec2 position. And I suppose for vec2, we need to have mymath.h. And I suppose we want to have a void function that says do text in a position and taking in a char pointer to a text. In order to store labels, we need what is called a struct UI state. And this UI state contains the uint32t label count and a label array labels of, I guess, a maximum amount of labels. So max labels. And I suppose we will just define that as a uint32t const expression max labeled to be 100. Don't forget the semicolon in the UI state. And I know this is weird, but I'll just add it in here. We will have to update UI, taking in a UI state pointer, UI state. And we'll get to why we need that. And I suppose when we want to add or do a text, we also need to supply the UI state pointer, UI state. The UI state will keep track of texts, and if we cannot add a text anymore, we'll just do nothing. I don't think we'll ever be above 100 texts, but who knows, right? And the way this works is, in this game, very simple. There will only be statically defined strings inside the code. Meaning, if I define, let's say something like this, a char pointer test to be hello, then this string, this pointer to a character array is stored in a separate memory location of the program. And for every single one of those characters, they are stored there. So if I have another point in my program where I have a char pointer to test 2 that says hello, it's likely, and I'm not 100% sure, but it's very likely that the same memory location is being addressed here, meaning that this string is only stored once in memory somewhere, and that never goes away. And this memory location here, this pointer to the memory location, is most likely the same. They both reference the same memory location. And these are going to be the only strings that we will use. I will hard code these strings into the game. If you want to have dynamic strings, you will probably have to deal with dynamic allocation of memory and adding dynamic strings in. But for Pong game, I don't think that's needed. You will have like a victory screen, you will have a player screen, and then you will display some time. And we'll get to all of that. So yeah, we'll have the char text here, the doText function, and the update UI. Next, we create a ui.cpp, which just includes the ui.h function, not function, but file. And then I guess we implement for functions. Update UI will only do one thing, UI state, UI state, label count to 0. That's what it will do. And then the doText checks if it can get one. So basically if UI state, and I suppose I could call this UI, it's a bit easier. I think I like calling it UI. Change that if you want to UI. I'll do that real quick. And the UI label count is less than max labels, if that is the case. Otherwise, I want to do a cakes search 0 and then say reached maximum amount of labels. And if not, we get the label pointer L to be L is the address of UI labels on UI label count plus. And then we set the L text to the text and the L position to the position. And so what is this? What does this do? How does that help us? Why would we set the label count to 0 every frame? This is what is called immediate mode UI. And now I know this is just for text, but we will extend this to buttons later on. What this means is every frame, we forget about the previous frame and we generate an entirely new UI. And for text, that's very simple. Every time we go through our game loop and we want to display a text every frame, we just say do text. Boom. And then we'll display the text every frame. So that allows us to be very dynamic in when and where we display text. And UI elements for that matter later on. Okay, let me see. We have the UI done. And I suppose we can include that in the game. Include UI.h. And I think this is the correct location, if I spell that correctly. A, B, C, D, F, G, H, I, J, K, L, M, P, Q, R, S, T, U, L, M, yeah. And I suppose that's in UI folder, UI.h. Once we have that included, we go to update. We go down to update game. And every time we update the game, we also want to do a text. Now we need the UI state for this, UI. So I suppose this function will take in the UI state pointer. By the way, did I change this to UI? Quickly, if you want, go to UI.h and change the parameter names to UI. I just want to be consistent here. And then back in game, we do a text. At what position? I guess we'll put it at 100.f by 100.f. And what type of text? Well, we say Pong from scratch, exclamation mark. And this is it. Now, every time the game updates, we will display the text Pong from scratch. But we are not done yet. We need to add more stuff. In the Win32 platform CPP file, we need to include at the very top the UI layer. And I suppose where would that be? What should UI have access to? I think UI should not have access to assets functions that are private. Maybe not even game functions, but then the game could have access to UI. I guess I'll include it here. This is the UI layer. And this is like the downside of this approach, of the single file compilation unit approach. If we include the UI.cpp here, UI.cpp has access to every game function, even functions that are only included in the CPP file of the game, which can be a downside. Now, let me also set this is the assets layer. The upside though is that we gain a lot of speed when compiling our program. It's very fast. It's always the same speed. Okay, and then we go down to the main function, and I guess below the game state, we also create a UI state, UI, and set that to 0. And then in the running loop, before we update the game, we also update UI. Take in the pointer to UI. And then here would be the pointer to UI supplied to the update game function as well. Now, obviously, this shouldn't do anything because we are not drawing UI yet. But let me double check if this works. Seems to work. Okay, so nothing happens. Nothing is being displayed. We do a text every frame. Now we need to handle that in the renderer. So we go back to VK renderer. I suppose after entity rendering, we also do UI rendering. Wow. Create that local scope. I guess we check if we have a UI label count, and I guess we need UI here first, so apply that as well to VK renderer. I suppose after the game stage. Now we have access to UI, then we check if we have labels. Do we have them? If so, we need to loop through them. For UN32T, label index is 0, label edx is less than UI label count, and then label edx++. Okay, what do we need to do for every label? I guess we will add a render command for every single one of those labels. I guess first we take the pointer to the label, or maybe we can even copy that. The UI labels on label edx. Okay, what do we do with the label? Now, if you remember, for every entity, we add a transform. And this time, what we need to do is, since every single character is pointing animation index into the texture at a certain location, we need to add a transform for every single character in our text. And so we need to loop through those elements in our text, and not a for loop. I like doing it this way, and I know this is not perfectly safe. We do a while loop for every character that is the value of our label text. I guess it's l.text++. So basically, what does that do? We take the text pointer, we increase the pointer by 1, and then we take the value of that pointer and interpret that as a character. We are going through every character in the string until we reach the null terminator, which is basically 0, until we reach 0. So this assumes that my text is null terminated. This assumes that l.text is null terminated. That's very important. This could cause an error if it isn't. And then for every character, we need to check, well, if the character is the same as space, I like skipping, meaning continue. I do not want to draw nothing, so I skip. And if you remember what our width is for characters, we try to make a monospaced font, and therefore every character has a width of 5 or 3, right? Like 1 padding and then 3 pixels in the middle. We scaled that up to 15, and so we want to set the position of the label, the l.position on X. We want to increase that by 15 points. And we could also, you know, handle \n if you want. And then we can copy this real quick, and if we get a \n, then we don't take the X coordinate, but by the Y coordinate. We increase the Y by 15. But then we also need to set back the X coordinate. So the origin, call this float, origin X is l.position X. Now we can set the l.position.x to the origin. Good. When we continue. For every other character, what we do is we add a transform. VK add transform. We need a VK context. Next, we need a material index, and that is based on, let me see, UN32T. Let's get a material index. UN32T material edx. We get that by calling get material based on, I guess, the game state, based on the asset, right, font atlas. And what color? White by default is fine. We could also choose a different color. We can now also supply a color to the labels if you want to, right? Take that as an opportunity to make the labels colored if you want to. Now we get the material index and we add that to the transform. Material index. The asset type ID would be the asset right font atlas. The position would be the l.position, and the animation index would be C. Since we structured our font atlas to start on 0 and end on 127, we can just use the character as the index into it. And I suppose we could make a double check here real quick. If C is less than 0, we just continue. We don't supply anything. We could even assert here if we want to. Wrong. That's actually wrong. And for every single character, we do the l.position.x plus equals 15.5. And then in Win32, go back to Win32 platform, we need to supply the UI. Is it the second one or the third one? I guess it's the third one. That would be the address to UI. Okay, are we drawing it yet? Is it fine? Is that good? Let me see. We add transforms. Oh, we need a render command for every label, I suppose. Or do I do all labels at once? I guess I would do all labels at once, but I think for every label, a render command makes more sense. So I guess the material index is in here. Let me structure it in a way so that we can use color in the future. We get a material index. We have the correct material. We also need to get a descriptor, pointer, descriptor. That would be vk get descriptor, takes in the context and the asset type ID, which would be asset sprite font atlas context. So, and then we need a render command pointer, and we get a vk add render command. Actually, we don't need to put these in here. We can extract those out. We add the render command here, vk context, and that takes in the descriptor. So obviously I need to check here if we have a descriptor. We do this, we'll put all of this in here. So extract all of this out into the if we have a descriptor, and then we check if we get a render command. Yes. If RC, do we have one? We also put that into this check. And then for every label, we need to know how many instances we are drawing with this render command. And so that would be, let me see, down below, that would be RC instance count ++ down here. Let me double check if that works. I would like to extract this into a function, vk render text. I'll probably do that. Let me double check if that works. And it works. Lol. First try. Hell yeah, brother. Woo. Okay, I guess we'll quickly extract this into a function. Call this vk render text. vk context for sure, and the rest we'll see. And it will be below, not vk render command, vk add render command. It will be below vk add transform. Internal void vk render text, vk context, pointer, vk context. And then we'll see what we need. We definitely need the char pointer to a text. We need a vec to origin. Take the text. We create a float origin x to be origin x. And then instead of increasing the position here, we increase origin.x and origin.y. Same as origin.x here. Origin. And we set that to origin x back. I suppose we need the material index. Okay. UN32T material edx. And then we add the transform at the origin. Oh, we also need the render command, the one that we are changing. Render command pointer RC. We need to supply that, break this up. And then of course we increase the origin here. And I suppose I forgot the return type, void. I rewrote this. Make sure that it's void return type. And then for vk render text, what do we supply? The render command, the material index, the l.text, and the l.position. Oopsie, l.text has to be spelled correctly. Hopefully that works. Hell yeah, brother. Very nice. Now we have text in our game. And the next time, we will extend this to buttons and UI elements. We will basically create a UI that will be displayed when the game launches. And then when we press a button, this UI will then show the game. And when the game is over, or when we lose, it will display a game over state. Basically, it will be so game state and UI next time. Thank you all for watching, and I will now do the Git stuff. We do git add dot git checkout -b. That would be 14 UI. Git added font to the game. Mono spaced. Git push -u origin 14_UI. Boom. Supply password. Good. Thank you all for watching and see you next time. Bye.